In the spring of 1992, the Endeavour Space Shuttle stood poised on its launch pad at Cape Canaveral, Florida, ready for its maiden voyage. A daring mission awaited its crew, a rendezvous between two spacecraft in orbit to rescue a stranded satellite. Bruce Melnick, one of the astronauts aboard, described the challenge they faced. The satellite, intended for geosynchronous orbit over 22,000 miles above Earth, had been launched on an unmanned rocket that failed to fire its second stage, leaving it stranded in a useless 800-mile high orbit. The crew's task was to capture it with their bare hands and attach a new second-stage rocket to send it to its proper orbit. As the countdown neared zero, the shuttle prepared for launch. Helium and nitrogen purged the main engines, flight surfaces and gimbals were tested, and the shuttle was fully fueled, now under its own power, disconnected from the launch pad. With 10 seconds left, sparkler-like igniters fired beneath the engines to burn off stray hydrogen. Liquid hydrogen raced through the fuel lines, pushed by tank pressure, expanding into gas as it hit the engine nozzles. This gas drove a low-pressure turbopump turbine, accelerating hydrogen flow in less than a second. Then, the main oxidizer valves opened, unleashing the fuel's full power as liquid oxygen and hydrogen met in high-pressure turbopumps, boosting flow rates further. Flames erupted in the nozzles, initially orange due to low oxygen levels and combustion instabilities that caused the engines to rattle. The engines then shifted to open-loop control, no longer following a scripted startup, but adjusting valves based on pressure readings. Oxygen valves widened, transforming the flame into a hot blue as the engines throttled up. Unlike most rockets, the shuttle's main engines were offset, attached to the reusable orbiter rather than the expendable external tank. When the main engines ignited 7 seconds before launch, they bent the entire stack, a phenomenon NASA called twang, restrained only by hold-down posts anchoring the solid rocket boosters SRBs to the pad. The SRBs, the largest solid rockets ever built, stood 45 meters tall, filled with a rubbery mixture of 70% ammonium perchlorate oxidizer and 16% aluminum fuel. Ignition required a rapid chain reaction, initiated by a miniature solid rocket motor within the SRB, itself sparked by an even smaller motor. This main igniter, with a 40-point star-shaped orifice, ensured quick combustion across the fuel column. Safety mechanisms prevented accidental ignition, including a pin in the SRB's top skirt, removed by technicians to arm the detonator at T-5 minutes. 8 massive hold-down bolts, each 711 mm long and 88 mm wide, anchored the SRBs to the pad. Frangible nuts, designed to fracture on command, secured these bolts. On 2 occasions, some failed to break cleanly, but one autostud hang-ups didn't halt the launch. A redesign later ensured simultaneous detonation within 50 microseconds. 3 seconds before launch, the main engines reached 90% thrust, signaling the SRBs to ignite. Their 13,000 kilonewtons of thrust, nearly double that of a Falcon 9 first stage, propelled the shuttle upward. Solid rockets, unlike liquid-fueled ones, couldn't be throttled down once ignited, burning until all propellant was consumed. This posed control challenges, as the rocket's weight decreased while thrust remained constant, risking excessive dynamic pressure that could tear the shuttle apart. To counter this, the SRB's fuel column was shaped with an 11-point star in the upper section, transitioning to a tapered circular section, reducing thrust by 33% after 50 seconds to manage pressure. Paired fuel batches ensured consistent thrust between the 2 SRBs, while thrust vectoring via hydraulic actuators in the aft skirt provided 80% of the shuttle's steering power. 7 seconds after liftoff, at 140 km/h, The shuttle initiated a roll program, rotating 180 degrees and pitching 12 degrees to align with its. This maneuver, driven by SRB nozzle vectoring, reduced stress on the wings and gave the crew a view of the horizon. The launch pad's design, inherited from the Saturn V, necessitated this roll rather than reorienting the shuttle pre-launch. At 45 seconds, the shuttle broke the sound barrier, and the roar of the engines faded as sound could no longer keep up. The air rushing over the shuttle's thermal tiles sounded like a train in a tunnel, growing quieter as the atmosphere thinned. 2 minutes into flight, the SRBS fuel neared depletion. Sensors detected dropping chamber pressures, triggering separation. The nozzles returned to neutral, and 8 separation motors, 4 at the top and 4 at the bottom fired, each producing 96,000 newtons to push the SRBS away from the external tank. The explosive bolts holding the SRBS to the tank detonated, startling Bruce with a loud bang and a fireball from the separation motor's exhaust. The SRBS climbed briefly before falling back to Earth, deploying parachutes for ocean recovery and reuse. Meanwhile, the orbiter entered its second stage, powered by 3 main engines fed by the external tank's liquid hydrogen and oxygen. The ride smoothed out, but G-forces built, peaking at 3G, where the engines throttled back to protect the winged vehicle's structural integrity. The external tank, a compromise from the shuttle's fully reusable vision, was a massive, expendable structure, 47 meters long and weighing 33.5 metric tons empty. Its aluminum skin, reinforced with rings and stringers, insulated cryogenic fuel with a double skin, and 2.2 tons of orange foam. The liquid oxygen tank, smaller due to oxygen's higher density, sat atop the larger hydrogen tank to raise the center of gravity for flight stability. A load-bearing intertank absorbed compressive forces from the SRBS, while a 46 centimeters wide pipe carried liquid oxygen to the orbiter, equipped with anti-vortex baffles to prevent instability. Gaseous hydrogen and oxygen, tapped from the engine's cooling loops, maintained tank pressure. Main engine cutoff occurred at 28,000 km per hour, triggered by velocity or propellant sensors. Extra hydrogen ensured a fuel-rich shutdown to protect the reusable engines. Frangible nuts separated the external tank, which tumbled away, disintegrating during re-entry. Closing the orbiter's umbilical plates was critical for safe re-entry, a task never requiring an EVA but always planned for. Bruce, momentarily distracted by Earth's beauty, nearly forgot to photograph the tank for post-mission analysis. The orbiter's reaction control system, RCS, using hypergolic nitrogen tetroxide and monomethyl hydrazine, maneuvered the shuttle. These toxic fuels ignited on contact, stored in lightweight spherical tanks pressurized by helium. With 38 main thrusters and 6 vernier thrusters, the RCS offered precise control for docking and attitude adjustments. Fly-by-wire controls, interpreted by computers, managed the system, except for the manually operated landing gear to avoid cosmic ray-induced errors. On STS-49, the crew aimed to capture a stranded Intelsat satellite. 2 astronauts, Pierre Thaut and Richard Heeb, prepared for an EVA, entering the airlock in the middeck. The satellite, lacking docking points, required a capture bar, but initial attempts failed as it spun out of control. After 2 days of failed tries, the crew devised a bold plan, a 3-astronaut EVA, despite the airlock's 2-person design. With only 2 umbilical connections, the 3rd astronaut, Tom Akers, relied on internal life support, squeezed upside down into the 160 centimeters wide airlock. Bruce, a former Coast Guard helicopter pilot, operated the Canadarm, a 15-meter, 430 kilograms arm with 6 joints, capable of moving 30 tons in orbit, but too weak to support itself on Earth. Its wire grapple system secured the capture bar, allowing the astronauts to attach a new rocket stage, sending the satellite to geostationary orbit. Life support included oxygen and nitrogen tanks for a breathable atmosphere, with lithium hydroxide canisters scrubbing CO2. Fuel cells generated electricity and water, degassing excess hydrogen. Payload doors, made of graphite epoxy, opened to expose radiator panels for heat rejection. A hydrogen leak on STS-93, caused by a dislodged gold pin, highlighted maintenance challenges but didn't derail the mission. Re-entry began with a 22-per-minute burn of the orbital maneuvering engines, slowing the shuttle by 0.1 kilometers per second to enter the atmosphere at a 40-degree angle. Superheated plasma, reaching 1,650 C, blocked communications for 12 minutes. The shuttle's aluminum airframe, protected by 32,000 silica tiles and reinforced carbon-carbon panels, withstood the heat. Tiles, 90% air by volume, were coated black for heat dissipation or white for solar reflection, glued to Nomex felt to allow airframe expansion. Flexible silica and Nomex blankets covered less critical areas. At Mach 12, the shuttle banked side to side to adjust lift, with elevons working counterintuitively due to hypersonic drag. Air data probes deployed at Mach 3, aiding the final glide. The shuttle's delta wings, driven by Air Force requirements for 2,000 kilometers cross-range, made it an unwieldy glider. Training on modified Gulfstream jets prepared pilots for the steep 20-degree glide and 360 km/h touchdown. A drag chute, debuted on STS-49, allowed landings on shorter runways. The mission ended with the crew disembarking, the shuttle refurbished, and flown back to Florida atop a 747, ready for its next adventure.